6 episodes ago, I made you a promise. I drew a stock chart, I zoomed into it, and I said, this curve cannot be differentiated, not at any point, ever. Today, we finally prove it, and we prove something even stranger. Brownian motion hides 3 secrets. First, can you take its derivative? The answer is no, and the answer is violent. Second, can you measure its length? The answer is yes, but the answer is infinity. Third, when does it first hit a target? The answer is yes, and the formula will astonish you. 7 chapters: non-differentiability, first variation, quadratic variation, reflection and first hitting times, the Martingale property, and a theorem, Lévy's characterization, that ties every single thread together. Watch what we are about to do. We will zoom into the path 1,000 times, 1,000,000 times, and you will see why no tangent line can survive. We will measure its length and watch the number explode to infinity while the sum of its squared increments locks onto the elapsed time. We will ask when a stock first crosses a barrier, and we will answer by placing a mirror on the chart. Brownian motion is violent, and it is beautiful. By the end of this episode, you will see the single piece of mathematics that bridges Einstein's jittering particles, every option ever priced, and the diffusion models that generate images from pure noise. Let's begin. What does it actually mean for a curve to have a derivative? Think of a parabola. Zoom in on a single point. The closer you look, the more the curve becomes a perfectly straight line. That straight line is the derivative, the local slope, the instantaneous rate of change. This is the essence of differentiability. Now, what happens if we try the same thing with Brownian motion? The derivative is a limit, the slope of a second line as its 2 endpoints collapse onto each other. Numerator w of t plus h minus w of t, denominator h. For any smooth curve, this ratio settles down to a finite number. But the increment of Brownian motion, by its very definition, is a Gaussian with variance h. So its typical size is the square root of h. Divide that by h, and the typical slope becomes 1 over square root of h. As h shrinks towards 0, that does not settle. It explodes. Watch this fail in real time. Here is Brownian motion over 1 unit of time. Pick any point. Zoom in by a factor of 10. The curve is smaller, but the roughness has not gone away. Zoom in by another factor of 10, 100 times magnification, and the jagged pattern is still there, identical in character. Zoom 1,000 times, the wiggles remain wiggles. At every scale we look, the path looks exactly like Brownian motion, just resized. This is self-similarity, and it is why no tangent line can ever fit. A parabola, zoomed far enough, becomes a line. Brownian motion, zoomed at any scale, stays rough. The derivative simply does not exist. Paley, Wiener, and Zygmunt, 1933. With probability 1, every sample path of Brownian motion is continuous, but nowhere differentiable. The promise from episode 1, delivered. And this is only the first of 3 strange results. Here is the second question from episode 1. How long is a Brownian path? For any smooth curve, length is arc length, the integral of the square root of 1 plus the derivative squared, integrated from start to end. But we just saw Brownian motion has no derivative anywhere. Every tangent slope is infinite. Every integrand in the arc length formula blows up. The classical approach is stillborn. There is a natural alternative. Chop the time axis into n pieces. Add up the absolute sizes of the increments. That sum is called the first variation v sub 1. As n grows and the pieces get smaller, we would hope v sub 1 converges to something finite. That something would be the path's length. Let's find out whether it does. Each increment, w at t plus delta t minus w at t, is Gaussian with variance delta t. Its absolute value is a half-normal random variable. Its expected size is the square root of 2 delta t over pi, multiplied by the number of pieces. N times root 2t over npi equals the square root of 2nt over pi. That is the expected value of v sub 1, averaged across many Brownian paths. Now look at this formula carefully. It contains a square root of n. As n goes to infinity, it does not converge. It grows without any bound. Let's measure it on one specific Brownian path. With 10 pieces, the total jump size is about 3.3. 50 pieces, 6.1, it doubled. 200 pieces, 11.7, doubled again, 1,000, 25.5, 10,000, 79.9. And the theory says this keeps going. 100,000 pieces, 252. 1 million, nearly 800, 10 million, over 2,500. The closer we look, the longer the path gets. The length of a Brownian path in 1 unit of time is infinity. A stock price in 1 year travels infinite distance. Its trajectory cannot be integrated in the Riemann-Stieltjes sense. Any attempt to define an integral against a Brownian path using the Riemann sum we all learned in school fails. Our usual calculus is broken. But one road remains. What if instead of absolute values we take squares? One dimension up. From absolute values to squares. V sub 2 is the sum of the squared increments instead of absolute increments. Each squared increment has expectation equal to its time step. This is just the variance of the underlying Gaussian. Sum n of them, n times delta t equals t. The expected value is simply t, regardless of n. But what about the spread of V sub 2 around t? A Gaussian's fourth moment is 3 sigma to the fourth, which gives the variance of w squared equal to 2 delta t squared, sum in such independent terms. 2n delta t squared equals 2t squared over n. That variance shrinks to 0 as n grows. The mean stays fixed at t. The variance vanishes. Double n, and the scatter shrinks by root 2. 10,000-fold n, and it nearly disappears. This is what L squared convergence means. V sub 2 locks onto t. Let's watch the race side by side. On the left, V sub 1, which we saw diverge. On the right, V sub 2, which should lock onto 1. 10 pieces. V1 is 3.3. V2 is 1.5, quite off with large scatter. 50. V1 6. V2 1.1. 200. V1 11.7. V2 1.11. 1000. V1 25. V2 0.99. 10,000. V1 80. V2 1.01. V2 is locked onto t. Not just for this specific path. For every Brownian path in the mean square sense, the quadratic variation equals the elapsed time. The sum of squared increments forgets the randomness and reveals just the clock. Mathematicians write this remarkable discovery in a compact shorthand. dw squared equals dt, paired with two companion rules, dw times dt equals 0 and dt squared equals 0. This trio is called the Ito multiplication rule. In Leibniz's classical calculus, products of infinitesimals all vanish. Ito discovered that for stochastic differentials, one of them refuses to die. 3 lines of notation. One of them is the key that opens Ito calculus. One final surprise is waiting. If we try to compute an integral like integral w dw, Riemann sums give different answers depending on which endpoint you evaluate at. And the difference between them is never 0. It is exactly V sub 2, exactly t. That tax on the Riemann definition is where Ito's integral begins, episode 8. The third question from episode 1. What is the probability that a Brownian path reaches a given level? Given a barrier A, what is the chance the maximum of the path over 0 to t crosses A? Barrier options, knockouts, exotic contracts worth trillions depend on exactly this probability. Here are 50 Brownian paths, each running from 0 over 1 unit of time. The barrier sits at a equals 2. Watch which ones break through. 3 paths cross the barrier. Theory predicts about 4.5%, so 2 or 3 out of 50. This matches. Now the trick that cracked this problem. At the moment a path first touches a, reflect the rest of it. Flip it about the line y equals a. The reflected trajectory is also a valid Brownian path. This is the strong Markov property. For every original path that ends above a, there is an exact twin created by reflection, ending below. The matching is 1 to 1. So the probability that the maximum touches A is exactly double the probability that the final endpoint alone exceeds A. P of max Wt reaches A equals 2 times P of Wt greater than A, which equals 2 times 1 minus phi of A over root T. For A equals 2 and T equals 1. That is roughly 4.55%. Rare, but not negligible. This formula, first written down for random walks by André in 1887, is called the reflection principle. The first hitting time, tau sub A, has a precise distribution. It is the Lévy distribution. Its density is over root 2 pit cubed times e to the minus a squared over 2t. And here's the paradox. The probability of eventually touching any level is 1, but the expected time until you do is infinity. The word martingale sounds intimidating, but it describes the simplest kind of random process there is. Imagine a fair casino game, where each round you might win $1 or lose $1 with equal chance. Each round, the expected change in your wealth, given everything you have seen so far, is exactly 0. Your expected wealth tomorrow, given today, equals today. No drift, no edge, Formally written, the conditional expectation of x at time t, given all information up to time s, equals x at time s. That is a martingale. Just fairness. Across time. Brownian motion itself is a martingale. Starting from 0 on average, w stays at 0 forever after, no matter how far into the future. Here is the ensemble average of 20 paths. Each individual path wanders wildly, up and down. But their mean, the gold line, stays pinned at the starting value. This is the signature of a martingale. Individuals run free, but the ensemble never drifts. Now the first real surprise, not only is w a martingale, the quantity w squared minus t is also a martingale. This is the same fact we proved in section 4, viewed from a completely different angle. The quadratic variation of w equals t, subtract t, and what remains is a fair game. And there is a third, the exponential martingale, e of e to the lambda w minus half lambda squared t equals 1 for every lambda and for every t 3 martingales, born from a single Brownian motion. These three quantities support essentially every pricing formula in modern quantitative finance. One final gift from this theory. If you choose when to stop playing, using any rule whatsoever as long as it looks only at past information, the expected value at the moment you stop still equals the starting value. You cannot beat a fair game with clever timing. This is Dube's optional stopping theorem, and it is the foundation of episode 12, Risk-Neutral Pricing, the mathematical engine of black skulls. We have reached the end. Today, we have seen 5 faces of Brownian motion. It is continuous but nowhere differentiable. Its first variation is infinite. Its quadratic variation is exactly t. Its maximum satisfies the reflection principle, and it produces 3 fair games. Which of these structural properties taken together uniquely define W? The answer is remarkably simple and remarkably small. In 1948, Paul Lévy proved one of the most elegant theorems in probability. If M is any continuous martingale starting from 0 and its quadratic variation is identically t, then M is a standard Brownian motion. Gaussianity, independent increments, everything else follows. 2 structural properties and W is uniquely fixed. This is the fingerprint, and continuity matters. A compensated Poisson process is also a martingale, but its jumps break the quadratic variation condition. Without continuity, the fingerprint does not match. And now for something extraordinary. Consider this single equation, dx equals fdt plus gdw, the universal Ito SDE. On the left, finance. A stock price follows ds equals mu sdt plus sigma sdw, geometric Brownian motion, driven by exactly the w we just characterized. On the right, AI image generation. Modern diffusion models, stable diffusion, DAL-E, Midjourney, add noise to an image step by step using exactly this equation. X at time t equals root alpha bar times x0 plus root 1 minus alpha bar times epsilon. Watch the image dissolve into pure noise. The same W that moves stock prices now generates images. Anderson in 1982 proved that the reverse of this process is also an Ito SDE. A neural network learns to run it backward, turning noise into photographs. Here's what lies ahead. Episode 8 constructs the Ito integral. Using today's result, that first variation is infinite. Episode 9 gives us Ito's lemma, built on the rule, dw squared equals dt. And episode 12 introduces the Girsanov theorem, which rests on the 3 martingales we saw. Brownian motion is violent and beautiful, and as of today, entirely ours. Thank you for coming with me this far. See you in episode 8.